This video goes over hypergeometric distribution, its characteristics, and a few examples. So a hypergeometric distribution is similar to a binomial distribution in that it has two possible outcomes, success or failure. However, the binomial distribution depends on independent trials. The hypergeometric distribution relies on dependent trials. So for example, this would be taking something out of a bag and not replacing it. That means that your probability of success is going to change with each successive trial. The calculations of probabilities in a hypergeometric distribution require knowledge of combinations. So to calculate the probability of X successes in R dependent trials is given by this equation here. A is the number of successful outcomes among a total of n possible outcomes. Let's go through an example to see how that equation works. So say this past Halloween you went trick-or-treating and you came back with 6 chocolate bars, 7 bags of chips, 3 suckers, and 4 juice boxes. If you reach into your bag and grab 5 items randomly, what is the probability that you will get 3 bags of chips? So the first thing that we can decide, so we've got some variables here. We've got A, X, N, and R. Deciding what those are before we use the equation will help us to get everything in the right spot. I'm interested in the probability that I'm going to get 3 bags of chips. That is going to be my X value. So the A value is connected to how many bags of chips that I have to choose from. So I've got 7 bags of chips. Now my N value is going to be the total number of items that I have in my bag. So I can add my haul together. So 6 plus 7 plus 3 plus 4 would give me 20 possible items to choose from. And then the R value is the number of trials that I'm doing. So I'm grabbing 5 items randomly, so that is going to be my value for R. So what this is going to allow me to do is to substitute everything into my formula. So my random variable is X, which is the chips. That I want to equal 3. So then the first part in my numerator is 7, choose 3, times 20 minus 7, choose 5 minus 3, over N, choose R. Now in this formula, the 7 choose 3 is saying that I want 3 bags of chips from a total of 7. The next part, which is 13 choose 2, is just saying out of the 13 items left, I want to pick 2 of those. The last part is my total number here, which is 20 choose 5. And then calculating that all out, I end up with approximately 0.1761, or about 18%. So the numerator is the specific request, while the denominator is the general request. We have done this before, kind of unofficially in our combinations unit, probability with combinations. Now we're just putting a name on it and working on it in our distributions unit. Let's do one more example here. In this one, we've got 6 birds and 8 hamsters in a pet store. 5 pets are chosen at random for relocation to a different store. What is the probability that exactly 3 of the pets chosen will be birds? So I'm looking for birds. That is my random variable. That means that my X is going to be 3, and my A value is the number of birds that I have. My N is going to be the total number of pets that I'm choosing from, which is 14. And my R value is the number of trials or the number of items that I'm choosing. In this case is 3. Now that I have those items or those variables defined, I can substitute them into my equation here. So I have A choose X times N minus A over 5 minus 3. I think I have a variable incorrect here. Oh, 5 pets are chosen. So that means that my R value, that makes more sense, should be 5, okay, because I can't have 0. And then on the bottom, I've got my general request. So I have 14 pets and I'm choosing 5. Evaluating that all out and using my calculator, gives me approximately 0.2797 or about 30%. I would encourage you to do it on your calculator to make sure that you are able to use the choose function appropriately. I'm just going to fill in one more row here. We'd have 8 choose 2 over 14 choose 5. Okay. The last question that we're going to do in this video is just looking at expected value. So like the other distributions that we've looked at, we can also calculate the expected value of a hypergeometric distribution. Since the probability of success changes, we have to use a little bit different formula than the binomial distribution. So this is the formula here. Your R value times your A value divided by N. So in the Halloween example that we did, our number of trials was 5. This was our N. The number of successful outcomes was 7. This is our A. And then the total number of successes is going to be 20. That means that the expected value can be calculated below. So 5 times 7 out of 20. Okay. So in here, we're going to calculate the expected number of birds that are going to be relocated to a different store. So we've got 14 pets. This is our N value. We've got 5 that are being relocated. So this is our R value, same as before. And then we've got 6 total birds, which is going to be our A value. So we can use our formula that we have above, R times A over N, and substitute in our values. So 5 times 6 divided by 14, which gives us approximately 2.143. And if we scroll up, we haven't redefined our variables. Those are the same as we had before that we defined at the very beginning of our problem. One thing I'm just going to modify here, this says the total of number of successes. It's more accurate to say our total number of options or available spots there. Okay. So those are examples of the hypergeometric distribution and how to calculate the expected value using the hypergeometric distribution.